Alright, let's go. Number 10. The planet closest to the Sun. Mercury is a world that no rational scientist would have placed on a list of candidates for extraterrestrial biology. It is the smallest planet in our solar system, and also the closest to the Sun. Its dayside burns at temperatures above 800 degrees Fahrenheit. Its nightside drops to nearly -300. It has no atmosphere worth the name, no insulation against the radiation that pours out of its enormous nearby star, and no obvious water. For decades, the consensus was simple. Mercury is dead. It always has been. It always will be. And then, beginning in the early 1990s, the assumption began to break. Earth-based radar observations conducted from the Goldstone facility in California picked up something strange in the polar craters of Mercury. The radar signal at the bottoms of those craters whose floors have never seen sunlight because the axial tilt of the planet is essentially zero, came back bright. Brighter than rock. The kind of bright that means ice. In 2011, the National Aeronautics and Space Administration's Messenger spacecraft entered orbit around Mercury and confirmed it directly. There is water ice on Mercury, somewhere between 100 billion and 1 trillion tons of it, locked inside permanently shadowed craters at both poles. And on top of that ice, in many of those same craters, lies a thin layer of dark organic material. Carbon-bearing compounds, possibly delivered by comets and asteroids over the long history of the planet. This is what scientists who study the origin of life call cold trap chemistry. Water plus organics, locked together in a stable, dark, isolated environment. It is not habitability in the ordinary sense. Mercury has no liquid water, no obvious energy gradient, no continuity, but the ingredients are there. And if the ingredients are there on the planet closest to the Sun, the question of where they are not is the more interesting one. Mercury is not where life lives. Mercury is the proof that we have been counting the wrong worlds. Number 9. A dwarf planet with a salty ocean. Between Mars and Jupiter lies the asteroid belt. Most of what is in it is exactly what we expect. Small, dry, irregular fragments of rock and metal, the leftovers of a planet that never finished forming. But one object in the belt is large enough to have pulled itself into a sphere under its own gravity. Its name is Ceres. It is the largest object between Mars and Jupiter. It is, technically, a dwarf planet. And in 2015, when the Dawn mission entered orbit around it, what it found was not what anyone had expected. Inside a crater called a crater, the surface of Ceres held two enormous bright spots. From orbit, they looked like floodlights shining out of a gray landscape. Dawn's spectrometer identified them as deposits of sodium carbonate, magnesium sulfate, and ammonium chloride, minerals that on Earth precipitate out of evaporating salt water. They were the residue of a brine. A briny liquid had risen up from below, reached the surface, frozen and sublimated, leaving the salts behind. In another crater, called Ernetet, the same spectrometer found organic compounds, carbon-rich molecules embedded in the surface material, identified as aliphatic hydrocarbons. The discovery was published by Maria Cristina de Sanctis and her colleagues in the journal Science in 2017. Earlier, in 2014, the European Herschel Space Observatory had detected actual water vapor escaping from the surface of Ceres, about 6 kilograms per second, suggesting either active venting or persistent sublimation from somewhere just beneath the crust. Gravity data from Dawn confirmed it. Ceres has a partly differentiated interior. Rock at its core, a layer of ice above that, and somewhere between the two, a global reservoir of briny liquid water. A subsurface ocean on a body that is not even officially a planet. Ceres is small. Its ocean, compared to the great oceans of the outer solar system, is small, but in every chemical sense, it is one of the closest watery worlds to Earth, and we have been ignoring it for most of the history of astronomy. Number 8. A world beyond the edge of the Sun. Pluto. For most of the 20th century, Pluto was the boundary marker, the small, cold, frozen dot at the edge of where the solar system was supposed to make sense. In 2006, the International Astronomical Union demoted it from planet to dwarf planet. In 2015, the New Horizons spacecraft, after a journey of 9.5 years, flew past Pluto at speeds of nearly 14 kilometers per second and sent back the first close-up photographs of a world that no human eye had ever clearly seen. What it sent back rewrote the textbook. Pluto has a heart-shaped feature on its surface, named Sputnik Planitia. The plane is composed of frozen nitrogen, layered hundreds of meters deep, and it is geologically active. The ice flows. There are convection cells the size of small countries on its surface, slowly turning over like simmering broth. There are mountains of water ice that rise 3 kilometers above the plane. There are cryovolcanoes, Reitmans, and Picardmans, large enough that geologists believe they are powered by something liquid moving beneath the crust. And the math, when scientists ran it, suggested something extraordinary. Pluto is too small, too far from the sun, and too old to have retained any meaningful internal heat by now. According to standard thermal models, it should be solid all the way through. But the surface activity is real, and the only way to explain it is if there is a layer of liquid, almost certainly briny, ammonia-rich water, beneath the ice. A subsurface ocean, on Pluto, 3.5 billion miles from the sun. The mass anomaly under Sputnik Planitia, the cryovolcanism, the smooth, fresh terrain, the ammonia detected on the surface ice, all line up with the same answer. Pluto is wet inside. If it is wet inside, the question of whether it is habitable is open. There may be no energy source. There may be no chemistry. But for an object we used to think of as a frozen rock, that is a remarkable thing for the data to be saying. Number 7. A captured moon, around an ice giant. Far beyond Pluto, around the planet Neptune, orbits a moon called Triton. Triton is unusual in the solar system for one specific reason. It moves backwards. Its orbit is retrograde, opposite to the rotation of the planet it orbits. Every other major moon in our system goes the way its planet spins. Triton does not. The mainstream explanation is that Triton was not born around Neptune. It is a captured object, almost certainly a former Kuiper Belt body that billions of years ago came too close to Neptune's gravity and was dragged into orbit, fundamentally changing both its trajectory and its history. In 1989, when the Voyager 2 spacecraft passed by Neptune on its grand tour of the outer planets, it photographed the surface of Triton. What it photographed had not been expected. Triton is one of the coldest objects ever directly observed in our solar system. Its surface temperature drops to around minus 235 degrees Celsius. It should, by every reasonable model, be utterly geologically dead. It is not. Voyager 2 captured images of active geysers, plumes of nitrogen gas, mixed with dark organic dust, shooting up to 8 kilometers above the surface. The plumes were visible. The gas was venting in real time. Triton was alive. Subsequent analysis confirmed that the surface of Triton is geologically very young, somewhere between 10 and 100 million years old, in a solar system older than 4.5 billion years. Something inside that moon is keeping the surface fresh. And the leading explanation, though still under investigation, is that Triton, like Pluto and Ceres, has a subsurface ocean of liquid water heated by some combination of radioactive decay in its core and tidal forces from Neptune. The mission concept Trident, proposed by the Jet Propulsion Laboratory, would have flown a spacecraft past Triton in 2038. It was not selected for funding, so we do not yet know. But if the inside of Triton is a wet, warm, organic-rich ocean, and if Triton is, in origin, a Kuiper Belt object, which means there are millions of similar bodies in the outer solar system, then we have not been counting the right number of habitable worlds in our own neighborhood. Number 6. The largest moon in the solar system. If you walked across the surface of Ganymede, Jupiter's largest moon, and in fact the largest moon in the entire solar system, you would be walking above an ocean larger than every body of water on Earth combined. Ganymede is bigger than the planet Mercury. It has a metal core, a rock mantle, and stacked layers of ice and liquid. According to current models, it may contain more total liquid water than every ocean, lake, sea, and aquifer on the surface of our home planet. The strongest direct evidence for Ganymede's subsurface ocean came in 2015. Joachim Saur, a planetary scientist at the University of Cologne, used the Hubble Space Telescope to observe the auroras dancing around Ganymede's poles. Ganymede has its own intrinsic magnetic field, the only moon in the solar system known to generate one. Auroras occur where its field intersects Jupiter's much larger magnetic environment. By measuring how those auroras moved, Saur and his team were able to detect the influence of an electrically conductive layer beneath the moon's icy surface. The layer behaved like a salty ocean. It had to be salty water, and it had to be deep. Their best estimate placed the ocean roughly 150 kilometers below Ganymede's outermost ice shell, with the ocean itself at least 100 kilometers thick. Later modeling has suggested that Ganymede's interior may be layered, multiple ocean layers separated by ice, like a stack of frozen sandwiches, each with its own chemistry. In April of 2023, the European Space Agency launched the JUICE mission, the Jupiter Icy Moons Explorer, toward this very moon. JUICE arrives in 2031. It will go into orbit around Ganymede in 2034. It will be the first spacecraft in history to orbit a moon other than Earth's own. Whatever it finds, it will find it in a place with more potential biological habitat, measured purely in volume of liquid water, than any other location currently known to human beings, including the Earth itself. Number 5. A hellscape that may be hiding microbes in the sky. Venus, the second planet from the Sun. Earth's closest neighbor and Earth's chemical sister. The planet that astronomers, before the space age, believed might be a tropical paradise. A younger, warmer Earth covered in jungles or oceans. The planet that, when the first Soviet and American probes of the 1960s and 70s actually landed there, was confirmed to be one of the most violently hostile environments in the solar system. Surface temperature, 900 degrees Fahrenheit, hot enough to melt lead. Surface pressure, 92 times that of Earth, equivalent to being a kilometer underwater. Atmosphere, 96% carbon dioxide. Clouds, pure sulfuric acid. The surface of Venus is closer to the standard description of hell than any other place humans have ever studied. But there is a layer in Venus's atmosphere, about 50 kilometers above the surface, where the temperature drops to between 0 and 70 degrees Celsius and the pressure is roughly equal to sea level on Earth. It is, in physical terms, perhaps the most Earth-like environment in the solar system outside of Earth itself. In 1967, Carl Sagan and Harold Morowitz proposed that microbial organisms could, in principle, be drifting through that exact cloud layer. In 2020, an international team led by Jane Greaves of Cardiff University announced in the journal Nature Astronomy that they had detected phosphine gas in the cloud layer of Venus. Phosphine is a single phosphorus atom bonded to 3 hydrogen atoms. It is significant because on Earth, phosphine is produced almost exclusively by anaerobic biological processes, by the metabolism of bacteria living in oxygen-free environments such as swamps, sediments, and the digestive tracts of penguins. The detection has been argued about, refined, partly retracted, and partly defended. Subsequent observations have detected the gas at lower concentrations, and others have challenged the detection entirely. The scientific community is divided, but every major space agency on Earth is now planning a return to Venus. NASA's Da Vinci probe is scheduled for 2029. NASA's Veritas orbiter will follow. Rocket Lab is sending a private mission. Russia is building Venera D. India and China are studying their own. The question is no longer whether Venus is dead. The question is whether we already missed life there once. Number 4. The only other world with stable liquid on its surface. Saturn's moon Titan is, in many ways, the strangest place on this list. It is the only world other than Earth in our solar system with stable liquid pooled openly on its surface. Lakes, rivers, seas. They have been photographed, mapped, and named. Kraken Mare, Ligeia Mare, Punga Mare. They are not lakes of water. They cannot be. Titan's surface temperature is around minus 179 degrees Celsius, far below the freezing point of any aqueous chemistry. They are lakes of liquid methane and ethane, a hydrocarbon hydrology, a complete, functioning planetary system of weather, evaporation, rainfall, and collection, but built around hydrocarbons rather than water. In January of 2005, the European Space Agency's Huygens probe, released by the Cassini spacecraft, descended through Titan's thick orange atmosphere and landed on its surface. It returned the first and so far only ground-level photographs of the surface of a moon belonging to another planet. The landscape was eerily Earth-like, rounded pebbles of water ice on a flat plain, evidence of fluid erosion. Titan's surface features were carved by liquid flow over geological time, just like Earth's. Only the fluid was wrong. In 2005, Christopher McKay of NASA Ames and Heather Smith of the International Space University proposed a hypothesis. If life exists on Titan, it would not be water-based. It would be methane-based. Such organisms, McKay argued, would consume hydrogen gas at the surface and react it with acetylene to produce methane, which they would then exhale. When the Cassini spacecraft analyzed the actual atmospheric composition near Titan's surface, the results, published by Darrell Strobel and others between 2010 and 2012, were unsettling. Hydrogen was being consumed at the surface, flowing downward instead of accumulating. Acetylene was scarcer than predicted. Both findings were consistent with the exact metabolism that had been hypothesized for a methane-based biology. Neither finding has yet been satisfactorily explained by non-biological chemistry. In 2028, NASA will launch the Dragonfly mission, a nuclear-powered, helicopter-style rotorcraft designed to fly across Titan's surface. It arrives in 2034. It will be looking for the answer. Number 3. The world that may already have answered us. Mars, the 4th planet from the Sun. The world humans have looked at, named, mapped, and projected our hopes onto more than any other body in the sky. The world where we have landed not one, but more than a dozen successful spacecraft over the past 60 years. The world that, at this moment, has 2 operational rovers on its surface, an orbital fleet circling above it, and a sample return mission in active preparation between NASA and the European Space Agency. It is also the world where, in 1976, the Viking One lander conducted an experiment whose results have never been satisfactorily resolved. The labeled release experiment, designed by the biochemist Gilbert Levin, consisted of dropping Martian soil into a small chamber of nutrient broth tagged with radioactive carbon. If anything in the soil metabolized the broth, the chamber would detect carbon dioxide gas labeled with that same radioactive signature. On July 30th, 1976, Viking One's chamber lit up. The reaction came quickly. It came strongly. It produced exactly the kind of curve that on Earth would have been classified as biological without question. NASA, looking at the broader chemistry of the Martian soil, concluded that a perchlorate-based oxidation reaction was the more likely explanation. Levin disagreed. He spent the rest of his life, until his death in 2021, publishing peer-reviewed papers arguing that Viking One had detected life on Mars in 1976 and that the world had failed to listen. In the years since, more anomalies have piled up. Methane spikes in the Martian atmosphere, detected by both ground-based observatories and the Curiosity rover, that rise and fall on a seasonal cycle the way biological emissions on Earth do. Recurring slope lineae, dark streaks that flow down crater walls, possibly indicating briny liquid water at or near the surface. Strange tubular structures and what some researchers, controversially, have argued resemble fungi. Photographed by Curiosity in Gale Crater. None of these findings is conclusive on its own. Together, they form a pattern. The Mars Sample Return mission is currently scheduled to bring sealed Martian rock cores back to Earth in the early 2030s. If those rocks contain biosignatures, the announcement that follows will be the announcement that ends one era of human history and begins another. Number 2. The ocean with more water than Earth. If life exists somewhere off the Earth in our own solar system, the most plausible single location, by the consensus opinion of the planetary science community as it stands today, is Europa. Europa is the second of the 4 large moons of Jupiter. It is slightly smaller than the Earth's moon. Its surface is the smoothest large surface in the solar system, polished flat by the continuous re-icing of its outer shell. The surface is laced with reddish-brown cracks that look, from orbit, exactly like the fracture patterns of pack ice on a frozen Arctic sea. The reason for that resemblance is that Europa is a frozen Arctic sea. Except the ocean below the ice is not local. It is global. It is 2 to 3 times larger by volume than every ocean on Earth combined. It is 10 to 15 kilometers deep on average, and it sits on top of a rocky seafloor where, almost certainly, there are hydrothermal vents pumping mineralized water into the sea. This matters for a specific reason. On Earth, the kind of life we suspect was the very first kind to evolve. Chemoautotrophic life, the kind of organism that does not depend on sunlight but instead derives energy from the chemical disequilibrium between hot mineral water and cold ocean water, lives at hydrothermal vents on the seafloor of our own oceans. If the same chemistry exists at the bottom of Europa, then the same biology, in principle, could have begun there. In 2012 and 2016, the Hubble Space Telescope detected what appeared to be plumes of water vapor erupting from cracks in Europa's surface, geysers, possibly venting material directly from the subsurface ocean into open space. If those plumes are real and continuous, they are essentially free samples of the ocean, available to be sniffed by a passing spacecraft. On October 14th, 2024, NASA launched the Europa Clipper mission. The spacecraft will arrive in the Jupiter system in 2030. It will fly through those plumes. It will analyze them with a mass spectrometer designed to detect organic molecules. By the early 2030s, we will know whether the largest body of liquid water in the inner solar system contains the chemistry of life. If it does, we are no longer alone. If it does not, the silence will be far louder than the silence we have now. Number 1. The moon where the chemistry already speaks the language of life. Of every world on this list, the one for which we have the most direct, the most damning, and the most quietly extraordinary evidence of habitability is not Mars and not Europa. It is a small, bright, quiet moon of Saturn. Its name is Enceladus. It is roughly 500 kilometers across, small enough that you could drive across it in a few days, if there were a road. And in 2005, the Cassini spacecraft, while flying through the Saturnian system, photographed something on its south pole that no one had been expecting. Plumes of water vapor were erupting from cracks in the surface. the so-called tiger stripes of Enceladus's south polar terrain. Hundreds of them. Continuous, reaching hundreds of kilometers above the surface. The plumes were not a fluke or a one-time event. They were a permanent feature of the moon. Cassini did the only thing a spacecraft can do in such a situation. It flew through them. The chemistry it sampled was, in retrospect, the most consequential measurement of the Cassini mission and possibly of any planetary mission ever flown. Inside the plumes, the spectrometers found water ice, sodium chloride, ammonia, carbon dioxide, methane, molecular hydrogen, and complex organic compounds, including molecules with masses above 200 atomic mass units, ranked among the largest organics ever directly detected outside the Earth. The discovery of those complex organics was published by Frank Postberg and his colleagues in the journal Nature in 2018. The molecular hydrogen finding, published a year earlier by Hunter Waite and his team in the journal Science, was particularly important. Hydrogen at that concentration could only be produced by hydrothermal reactions between hot rock and liquid water at the bottom of an ocean. It is the same chemistry that powers the chemoautotrophic ecosystems at the deep-sea vents on the ocean floor of the Earth. It is, in plain words, food. NASA, in its press release announcing the Waite paper, used a phrase it does not use lightly. The agency stated that Enceladus has the chemistry necessary to support life, and that the moon is therefore, in the formal scientific sense of the word, habitable. The plumes are still erupting. The ocean is still there. We have not yet sent a mission specifically designed to look for life inside it. But the Enceladus Orbolander mission, currently a top recommendation of the Planetary Science Decadal Survey, would do exactly that. Orbit the moon, fly through the plumes, and eventually land near them and sample them directly. If life exists anywhere off the Earth in our own solar system, the strongest case is Enceladus. The chemistry is right, the energy source is right, the water is right. The only thing we have not yet confirmed is whether anything is using those ingredients. The table has been set. The question is whether someone is already eating. Closing reflection. We have spent the entire history of the human species looking up at the sky and asking the same question. Are we alone? The answer, for thousands of years, was assumed to be silence. The answer for most of the 20th century was assumed to be that we would never know. But mission after mission, decade after decade, the answer is quietly becoming something different. Within a few 100 million miles of where you are sitting right now, there are at least 10 environments in which life, by every chemical and physical standard we currently recognize, could already exist. We have not visited most of them. We have not even seriously looked. Over the next 20 years, that will change. Spacecraft are en route to Europa and to Triton. Probes are being designed for Enceladus. Missions are being prepared for Venus. By the year 2040, we may know. The silence we have lived in for the entirety of our recorded history may be ending, and we will have to learn, at last, what kind of universe we have actually been living in all along.